Now time for our third speaker, Professor George Rzevski. Professor George Rzevski is Emeritus Professor of the Open University, Milton Keynes, UK, where he has been involved in research in complexity science, multi-agent technology and mechatronics. Professor George has served as visiting professor at the London School of Economics, the University of Applied Sciences, Cologne, Germany, Brunel University, West London, Wuhan University, China, Samara Aerospace University, Russia, and at the University of Moratua. Professor George is also the founder and chairman of a number of international companies based in the UK, USA, Russia, and Germany, developing and marketing large-scale multi-agent systems for applications such as real-time logistics, semantic search, and dynamic data mining. He has published widely and has delivered keynote papers at numerous international conferences. He has 3 UK and international patents on multi-agent systems for logistics, dynamic data mining, and semantic processing. He served as editor-in-chief of the Journal of Artificial Intelligence in Engineering, published by Elsevier. And today, Professor George will speak on complexity science and knowledge technology for defense industry and military forces in the 21st century.
Thank you, Chair. I can see a lot of familiar faces. How many of you have attended my workshop? Not that much. Those who have will know this subject better than me. So you will help them with questions and comments, I'm sure. So let's talk about complexity science and knowledge technology and how they can be applied in defense industry and military. That was the brief which I was given, and we'll see whether I'll make sense. Complexity science is a very new science. It is about very complex systems, and I'll better show you immediately examples. Systems such as human brain, the most complex system that we know. Global digital network, which we are building and which soon will approach complexity of the human brain. Geopolitical systems, extremely complex, particularly now. We had a fantastic, simple situation, Eastern Bloc, Western Bloc. Weapons like that, and everything safe. Now, engage in religious, regional wars, and complexity science can actually help understanding results of these conflicts. If I have time, I'll maybe come to that. The internet-based global market, we have billions of people trading with each other over the internet. Suppliers, users, customers, buyers, consultants, all engaged in making transactions and changing them. By the way, I'm walking. Can you hear me when I walk? Okay. So, it's another complex system which I have looked at. A much smaller but extremely complex system is coordination of power, communication, and weapon systems on a military ship. A battle I've looked at Napoleonic Wars, and Napoleon was always under the impression that he gives command which are obeyed, but in fact, by the time instruction comes to somebody, it's too late. The situation has changed. Very complex situation, not linear at all. Life of an aircraft, a global supply chain. I've helped a lot of businesses in coordinating transportation through a huge global supply chain. Teamwork, natural language conversation, assigning meanings to words, and semantic processing, very complex. And big data, that's something which is currently very important. We are collecting data, and we have to extract knowledge from this data in order to be able to understand what is happening in this connected world. So these are the examples of complexity science. To start with, complexity science is interested not just in behavior, but how this system became what they are. There is a philosophical difference between Newtonian physics, say, which is based on the assumption that the world is deterministic and that if you have some uncertainty about what is happening, it's because we haven't enough knowledge. Now, complexity science considers that the world is constantly changing, evolving, and therefore there is a bound to be uncertainty about the future. Never mind whether we can learn enough or not. We just simply cannot know what is going to happen because it is not given, but determined. It is a result of evolutionary process. So a complex system normally consists of a very large number of components, has no centralized control. Behavior emerges from interaction of components, which are normally called agents. And it's unpredictable. We cannot predict outcome of a battle. We cannot predict even outcome of an economic situation in which we constantly, under new circumstances, in the global market, have unexpected orders or expected orders are not coming, failures, delays, which are called disruptive events that are hitting business all the time. However, complex systems are adaptive. They are capable of self-organizing to adapt to changes in their environment. That is something which we really have to cherish. This is a wonderful quality of complex system, that they can adjust themselves, neutralize disruptive events. Now to do that, you have to have intelligent components. Basically, this is either human beings or software with artificial intelligence. These are two best known examples of intelligent agents that can adapt without intervention from the outside to disruptions. And there is, of course, this quality of which we call creativity, autonomously to innovate, do something differently in order to improve performance. And here, of course, human brain is on the top. But we are designing software capable of capable of actually starting a process of improvement of performance without being instructed by programmers. And there is a weakness, and danger, and risk, and that is that because of non-linearities of connections, small disruptions can cause extreme events. Tsunami is a natural example of that. But also we have financial crisis which nobody could have actually pointed who was responsible for this crisis. There were so many little things done that accumulated to a big crisis. So these are characteristic of complex systems, and we need now a new science to actually explain behavior of such systems. And there is at the moment in very large number of UK and American universities new courses on complexity science and even new departments. My university has a laboratory for complexity science now for 15 years. This global digital network that we are building is huge, and it's approaching complexity of the human brain. The first was Internet of Documents, where all texts, all books, all newspapers, all videos were digitized. Then came the Internet of People, which is by now 3 billion. But what Sri Lanka can take advantage of is a new trend, the Internet of Things. All machines, all devices, all vehicles, even animals who are of interest to humans are provided with electronic ducts that enable them to broadcast to the Internet and get in touch with other things. So you have cars talking to cars, cars talking to service stations without any intervention. For that, it requires software. And there is a notion in the UK certainly that the demand for programmers who can actually design software for this Internet of Things is growing exponentially considering the low available talent in the UK. So just watch and prepare yourself. Now, Internet users grow exponentially, and during the last 6 years, the scene is completely changed. So whatever I was doing 6 years ago, today not valid. Because complexity was particularly what I'm dealing mainly is the global network in economic sense, the global market based on the Internet. So with rush of new users, complexity is going up and up. The interesting thing is that it's not just Internet, 3 billion users, but it's 4.8 billion mobile users and only 4.2 billion toothbrushes. So we have an incredible, and Sri Lanka is a fantastic example where my students, which are the 6th year and my students were telling me that agriculture is full of illiterate people with mobile phones. So the best project that I have heard of launching is to design a system to warn farmers of approaching monsoons by transferring information into speech and telling them over the mobile phone. So, complexity of the internet approaching the complexity of the brain. Brain enables us to learn, to write. We are what our brain is. Now, can you imagine if outside us, the global network become as complex as brain and start showing ability to adapt, to change, to learn, and to be creative. It's not science fiction, although it may sound. Because neurophysiology tells us that really brain can function completely independently as a complex system. There is no need to think about anything else, just biological machine. Extremely complex and extremely powerful. So Internet created global village for us, created a rather complex global economy, but also brought risks of cybercrime, cyber wars. So I'll cover this if I have enough time. Time is flying. The thing to remember is that technology and society co-evolve. That society cannot stay as it is when the new technology arrives. So we in the West went through a phase of industrial society because we developed mass production technology. Now, when we have developed information technology, connecting things together, not only that, but being able to process knowledge. We now have technology that is capable of discovering knowledge from data, that is capable of storing knowledge, processing knowledge, and applying knowledge. Society cannot stay as it was. And if it attempts to stay unchanged, it will just fall back. That's life. 21st century is called by many eminent scientists as the age of complexity. And in the UK, the switch from industrial society to information society coincided with a huge increase in complexity of economy, social systems, and of course technology. And here is the list of all the technological innovations that brought this up. Technology is pushing society and pushing the economy to switch. We have in England 60% of our income is from knowledge services, selling knowledge, not goods. About 50 years ago, we had 60% of our income from selling goods. And Sri Lanka is in a wonderful position to avoid industrial age and switch from agriculture to information society. So I'll better come to some applications because I've run out of time. Actually, explaining such a complex concept in 30 minutes just not possible. So what we have found experimentally, that only complex system can function productively in complex environments. You cannot have a rigid system performing well if the environment is volatile, dynamic, changes all the time. You have to have adaptable system. You have to have a system capable of changing what it's doing to accommodate disruptive events. Therefore, we've had now to learn how to design complexity in our lives, in business, in military. And it is counterintuitive because every consultant tells you simplify. But if you simplify, you will not survive in a complex world. That is very much like Newton's law. You can't argue with that. You may not like it, but you have to have a complex business, complex military, in order to be successful in the complex world. So I have a number of case studies, and to start with, hierarchical systems behave poorly in complex environments. There is no time for information about sudden change to go up to the decision making and then to wait for instructions to come down. Absolutely no time. The world has moved while you are changing, while you are waiting for chief executive, say, or commander to instruct you what to do. There has to be change to network arrangement. And when you look at the human brain, it is a network, but it is always organizing itself, self-organizing into clusters, teams. Each team is performing something and coordinating that work with another team. And there is a knowledge base in our brain that is a genome, copy of a genome in every cell, which has instruction for self how to behave, how to make connections. Now, what we do in software, we collect knowledge, put in a knowledge base, so that agents can consult knowledge before they send messages to each other. So the whole problem is being solved by agents, therefore the components. It could be humans, it could be software agents, sending messages to each other. For example, I'm an order for transportation. Any truck available to get me there for that month? Truck agents would say, okay, I can do that, or I can't do that, I'm far away. So it is a conversational way of solving the problem, and that is the only way to cope with complexity. If you want to have a very complex algorithm, you will not get very far. And I'll show you one example at least where this is true, just to show you diagram of technology which we are using to design complex adaptive software. It's a multi-agent technology. Agent is a computational object, small, with access to knowledge, so that it has some intelligence, which send messages to other agents. And there is always coordinating agent, enterprise agent, which never issues orders, but coordinates work of agents. And there is always knowledge base for consultation. I have here several case studies. The International Space Station, for which my team in Russia has developed software, but go first to this one. It's a military application. I was invited by Marconi, who's supplied software for military ship. I think it was sold to the Navy abroad, and it didn't work. And it didn't work because algorithms did not coordinate shooting, communication, and power. When you start launching rockets, the ship has to be stable, and there should be no communication. But there are so many possibilities that programmers could not foresee all the possibilities to say to normally write a program, if then, if then, if then. So my advice was, you have three agents. One agent representing weapons, one communication, one power, and they talk to each other. Weapon agent says, I just got this instruction to shoot. Could you stop, please? And communication says, sorry, I can't stop now. I'm just receiving a message. In 3 seconds, I shall stop. Power says, I need a certain time for ship to stabilize when I stop. So it will not be less than 20 seconds. In no time, they have agreed at what point they are going and available to the attack. Which is absolutely incredible. The problem is hundreds of programmers do not devise an algorithm for almost a year on this. You could solve by negotiation between intelligence agents in a few seconds. I'll show you how it's done. You have 3 demands for action at a particular time, and they are overlapping. Communication, power, and weapons. And through discussions between agents, they manage to push blue to the left, yellow to the right, and red to the very right, and you have a solution. And this is universally true. Negotiation is better than aggression. Negotiation brings people to a peaceful agreement in various disputes, if properly conducted. But software can do that in action. I think people are very excited about negotiating with energy and so on. But software can do that in action. Just without any passion, without any prejudice. And the whole system looks like that. You have a ship with 3 systems, and it is in a particular state, and disruptive event means new instruction to do something. And you design a virtual world, virtual model of what is happening there, using multi-agent technology. And it will receive information about current state and disruptive event, and will calculate what is the best next state and send instructions to the real world. So the virtual world manages the real world. So technology actually for doing that, and experience exists in the UK, Russia, and Israel. But only a small team. That's an incredible potential for commercial exploitation. At Moratua. The second example, before I finish, is cyber war. As I said, the global network gave us a lot of opportunities, but also a risk of global war. However, you can actually defend yourself using the same technology. And you defend yourself by identifying defense points. You know, for any attack, electronic attack, there must be entrance point into your system. So you must identify all possible entrance points, monitor them. And if your monitoring system shows that something akin to unusual, akin to evidence, your multi-agent system works out how to organize resources to counter that particular attack. It sends information to you. And that is, we have tried this not on cyber war, fortunately, there wasn't one yet, but on hacking, on bank systems. You had hackers would attack during the night and open thousands of private accounts and transfer all the money somewhere and over. And lucky bank, it was a long time ago, so I said which bank was that. Just didn't do anything at the morning. Let them empty all the accounts because how do you know that somebody is attacking rather than people are still using overnight for online banking? Well, you know this if you have a monitoring system because nobody ever does that. 1,000 accounts open and everything transferred. That's unusual activity. And the key for stopping that is to spot unusual activity. So as soon as you spot unusual activity, you can close the site. You can do a lot of things. But the key is to spot early warning system to spot activity. And you can do that if you have technology to do it. So, Chairperson, do I have to stop now? Or how do it? It would be a good idea. So you had some glimpse into the power of new technology, which is developed in response to the complexity of our environment. And I hope Sri Lanka is going to take advantage of this knowledge which is in Moratua University.